In order that we may keep track of where we are, I've put on the board an outline of what we're going to consider. First, I would like to demonstrate to you some of the properties of semiconductors. Then I would like to present a simple model. Then we will take up just a little bit of the history of the development. And then some of the impact of the discoveries that came. And then some of the new phenomena. Semiconductors, as the name implies, are conductors of electricity. At first, materials were divided into two classes, those that conduct electricity and those that do not. These were called conductors and non-conductors, or if you wish, metals and insulators. Then it was found that there was an intermediate class of materials that did not conduct very well, but still were not good insulators. These are the semiconductors. I'm going to illustrate to you some of their important properties. I have here a small rectangular piece of a semiconductor connected in series with this battery and this meter. You can see that there is current flowing through this semiconductor. One of the first properties noticed about semiconductors was the fact that they have a negative temperature coefficient of resistance, that the current increases as you heat the sample. I have here a Bunsen burner with which I will heat this sample up a bit, and as you can see, the current increases quite a great deal. You notice that this definitely must be a heat effect because it takes a long time for that block to cool down. The current stays up after I take the flame away. To show you that semiconductors are distinctly different from metals in this respect, I have here a metal wire wound on this ceramic spool that I will put in place of the semiconductor. In this case, in order to get a resistance somewhat near that of that short, thick piece of semiconductor, I've taken a very thin wire, about 4 mils in diameter, and about 16 feet of it, and still it has a smaller resistance, more current than flowed through that short block of semiconductor. In this case, you will see that when I heat this metal wire, the current decreases. In other words, metals have a positive temperature coefficient of resistance. Another property of semiconductors is that the contacts to them sometimes pass current in one direction better than another. I have here a piece of semiconductor in which two contacts have been made to. One contact has these properties. The other contact is omitted. In order to illustrate this property of rectification, I have on the scope here presented a sinusoidal current. When I plug this semiconductor across here, I block the current flowing in one direction. Notice that this property has a definite sign. If I turn this over, it blocks the current flowing in the other direction. Another property that semiconductors have is that their conductivity is sensitive to light. If I reconnect this piece of semiconductor here in my circuit and turn the meter back down on the more sensitive scale, and then shine this light on the semiconductor, you see the amount of current that flows is greatly increased. This is a light effect and is instantaneous, you see, as I take my hand in and out of the light. Still another light effect is that if we shine light on one of these rectifying contacts, such as the one here, then I get a photo EMF. In this case, I don't need the battery. I just need to connect this piece of semiconductor with its contacts in series with the meter. I've connected it backwards, as you see, because this photo effect has a sign. But there's quite a bright light here, so you already see a reading on the meter. However, if I cover this up and put it in dark, you see the needle goes to 0. And if I put this strong light on it, I get a much larger signal, even off scale on this meter. This is the so-called photo EMF. Another property of these materials is that there can be an EMF between two contacts of different temperatures. I have here just an ordinary metal probe and another metal probe that's made in the form of a soldering iron so I can heat this point. Actually, contacts between metals have this property, but on a very small degree, and you can hardly notice when I put these two metals in contact any change on this meter. But if I put these 2 points down on this piece of semiconductor, you see the needle moves way over to my right. Here's another piece of semiconductor, exactly like that one, except that when I put the 2 points down on it, it moves way over to the left. This is called the thermal EMF. Here you see that two materials that are practically alike can have different signs of thermal EMF. Still another property that has a sign was that discovered by Hall. This property was that if one has a current flowing in a conductor and one places a magnetic field perpendicular to the direction of flow of the current, that then the current will be deflected. And that in order to keep the current flowing uniformly down the conductor, the sides of the conductor will become charged. Here again, in most metals, this property had one sign. But in the case of semiconductors, it was found that in some semiconductors it could have one sign, such as this, and others the opposite sign. These effects were all found before the 20th century, some on one semiconductor and some on another. After the discovery of the electron at the beginning of the 20th century, one understood the sign of the Hall effect in most metals, since it was postulated and believed that the carrier of electricity in metals was the electron. And in a situation of this kind, with the direction of flow of current in that direction, the electrons flowing the other way, the electrons would be deflected to the top, and the top would become negatively charged. But in the case of the semiconductors, where you could have either one sign or the other, this was hard to understand. But it was found that these different signs, the sign of rectification, the sign of the photo EMF, and the sign of the thermal EMF, and the sign of the Hall effect were all correlated. That if you knew one, you could predict the signs of the other. That if the sign of the thermal EMF was one sign, was negative, the sign of the Hall effect would be negative, the sign of the photo EMF would be negative, and the rectification would be in a certain direction, and if it vice versa, it would be the other way. Without worrying too much about the difficulty of this positive charge, we can construct a simple model to explain these experimental facts. This model consists of just forgetting about the difficulties and assuming that a semiconductor is a medium in which both these types of charges can exist. That these types of charges come from the dissociation of a chemical bond. That a chemical bond can dissociate into an electron, negative charge, plus a positive electron. That it takes energy to break a chemical bond and form these two types of conductors. And that in a normal semiconductor at room temperature, some of these bonds are dissociated by thermal excitation. We can get a little more detailed picture of what this shows by taking a particular semiconductor, a crystal made of germanium, in the fourth column of the periodic table, carbon, silicon, and germanium. We have shown here a two-dimensional representation of the germanium lattice. Germanium has 4 electrons, 4 valence electrons. It shares one of these valence electrons with each of its 4 neighbors. Here we have a chemical bond structure that can dissociate. When the chemical bond structure dissociates, it's the equivalent of taking an electron out of one of these bonds, leaving it free to move around the crystal to conduct electricity. But we've done something else to the lattice. We've got in the lattice a position, that bonding position, that's lacking an electron. And this bonding position can also move through the lattice in this manner. This electron here can move over and go into this one, and so on. So we have a medium in which, by dissociation of chemical bonds, we can have both free electrons to conduct electricity and free vacant positions in the lattice to conduct. These vacant positions are called holes. And we have a medium in which we can have both electrons and holes as carriers of electrical current. We need to go further, though, to get the model that we need to explain the experimental facts that we've seen before. To do this, we go over to the periodic table and pick out an atom from the 5th column, such as arsenic, as an impurity. When arsenic as an impurity occurs in the germanium crystal, it goes in substitutionally in the place of a germanium atom. The difference, however, here is that the arsenic has 5 valence electrons, and it only needs 4 valence electrons to make up these chemical bonds. Therefore, we have 1 electron left over that's free to wander around the crystal and conduct electricity. And this, as was first called, would be an excess semiconductor. There would be excess electrons left over from the chemical bonding structure. To get the other type, we go back to our periodic table and pick out an impurity from the 3rd column of the periodic table, gallium. Putting this gallium in instead of the arsenic, we then have a situation where we only have 3 valence electrons to fill the bonding structure of the crystal. In other words, we have a vacant position in the bonding structure or hole, and that this vacant position can move around. So here we have what has been called a defect semiconductor. There are not enough electrons to fill the chemical bonding structure. So we have now either a lattice that has extra electrons in it, and in the case of such a lattice, we have a negative thermal EMF, a negative Hall coefficient, and the corresponding signs of thermal EMF and rectification. If, on the other hand, we had a gallium-doped germanium lattice, we would have a defect semiconductor, and we would have the opposite signs of these various effects. In a situation of this kind, where we have a chemical equation showing a dissociation, we can write down a very fundamental law. If we take for the concentration of the free electrons in the crystal the number n, and if we take for the concentration of the holes or vacant bonding positions the number p, the law says that in thermal equilibrium at a given temperature that this product should be equal to a constant. As most chemists and physicists know, this constant has a very simple dependence upon temperature. K is equal to a different constant, K prime, times an exponential function of the negative of the energy necessary to dissociate this chemical bond, e.g., divided by Boltzmann's constant times the absolute temperature. The real part of the dependence of this equation on which particular semiconductor we took is how much energy was necessary to dissociate the chemical bond. If we had taken, instead of germanium, another semiconductor, the EG would be different. And this is about the only thing in this equation that would have been different. Here we see, then, we have a model for our phenomena. In the case where the crystal or medium is pure, N is equal to P. But in the case where there has been an impurity added, such as to give us extra electrons, then N is increased, but because of the necessity of the product being equal to a constant, P has been decreased. This is called an N-type semiconductor. N is greater than P. In the other case, where we put in an impurity atom to increase the number of vacant positions or holes, then we have a P-type semiconductor, and P is greater than N. With this simple picture, it becomes difficult to see why the fundamental phenomena of semiconductors were not understood sooner. There were many difficulties, however. One was the fact that the materials the experimentalists were working with were much more complicated than silicon or germanium. Copper oxide, for example, was a P-type semiconductor. It was difficult to find out what the essential impurities in it were. One could only make it by formula, by art. One could not control these impurities. It was a very highly P-type semiconductor. P was much greater than N, so much greater than N that the experimentalist had the tendency to forget about the fact that there might be some electrons, that the electrons might play a role. Other materials had N greater than P, but so much greater that there again the other carrier was lost sight of. Then there was the difficulty as to how these broken valence bonds could really take part in the conductivity. Why the movement of the place where the bond was broken through the lattice would not be very slow and sluggish, somewhat like the movement of a positive ion. It took the advent of quantum mechanics and the understanding of motions of electrons in a crystal lattice to remove this difficulty. The real big break came when one began to concentrate on the simpler materials like silicon and germanium, materials that are, after all, made up of single atoms, and one could control and find out what the impurity atoms in the crystals were. With the work on these materials and the beginning of understanding of the equilibrium phenomena in semiconductors, another phenomena came along, and that was the fact that while in equilibrium this law must hold, that one can momentarily, especially at surfaces, violate equilibrium and create extra holes and electrons. And with this discovery, of course, came the discovery of the transistor and the fact that one could make active circuit elements out of semiconductors. It became then important to make even better samples of semiconducting materials of silicon and germanium, such as these single crystals, this one of silicon and this one of germanium. These are crystals of a degree of perfection, samples of solids that have not been made before. Ordinary chemical purity is considered very good if one gets to a part in a million. But in these crystals, the impurity has been reduced to parts in 10 to the 9th or 10 to the 10th, way beyond a factor of 1,000 or 10,000 times more pure than the chemists had known before. This has had a tremendous impact upon the whole field of theory and experiment in solids. It was not until one got materials this pure that one could begin to look at and understand the imperfections that were still left, that they had been reduced to a point where one could count these imperfections and measure how they changed under certain conditions and really begin to understand what was going on. It would, of course, be very surprising if such an understanding would not lead to new phenomena. One such phenomena that was very interesting is that these electrons and holes in a crystal medium of this kind form, in the presence of a magnetic field, a natural resonant system, very much like a pendulum. The magnetic field tends to make the electrons and holes go in circles if they move at all. And the interesting part of this phenomena is that the resonant frequency is independent of the magnitude of the motion. Therefore, if one irradiates one of these crystals in the presence of a magnetic field with electromagnetic radiation of the proper frequency, one can measure this resonance. And, as one might expect, the magnitude of this resonant frequency is a measure of the effective mass of these carriers in this crystal medium. One is not surprised, after what one has heard, that this effective mass is near the mass of an electron in free space. What was surprising was that the mass can be much less, even 100 times less in some cases, than the mass of an electron in free space. This phenomena was called cyclotron resonance. Another area of interest concerns the optical properties of these crystals. They appear, as you see, to have a metallic luster, and they also appear to you to be opaque. These are essentially two different properties. The opaqueness is due to the fact that the energy necessary to dissociate the valence bond in these crystals is small enough so it only takes a quantum of energy in the near infrared. And in the visible, all the light is absorbed, creating whole electron pairs. The metallic luster, however, is due to the tremendously high index of refraction these crystals have. New materials have been found that take a larger energy to dissociate one of their valence bonds. Such a material is this piece that I have here in my hand. It also, as you see, has this metallic luster. But since the energy now is equivalent to a quantum in the near ultraviolet, this material is actually transparent, which can be seen if I place it here in the light of this lamp. The transparency of materials of this kind in the visible allows us to study another phenomena. We've discussed how whole electron pairs can be created by adding energy to these materials. The reverse process also occurs. When there are extra whole electron pairs in these crystals, they recombine and they give out light. That experiment can be demonstrated over here, where I have a battery in series with a small piece of this material, and by passing current through this material, I can create whole electron pairs, and by looking through this microscope, I can see the radiation of recombination of these holes and electrons. In concluding, I'd like to point out that we have been concerned here throughout with the subject matter of a given field of physics. There is a tendency when you are taking a physics course to be so concerned with the subject matter that you may overlook the really important part. Physics is not the subject matter of any given course. What is important to learn is any and all physical phenomena. I know of no other field which better illustrates the application of the full range of physics to the understanding of a given problem.